am Michael. I tried to make slides for this thing, but I figured out it would not be a really good idea because I would make it smaller and you will not see how much work you need to do to perform anomaly detection. It will just seem too easy, and then you will swear at me that I lied. So what we will actually see is that there's a notebook, so literally Google my surname, there's a GitHub. In there you will find a PyCon repository, and there's a huge notebook, Jupyter notebook in there, and we'll scroll through it. We'll jump a part that should be easy to figure out from the code, and we'll not actually run the code in there. The code is a way of cheating me, of I'm cheating, to tell you more than 20 minutes can allow me. So there's a lot of text there. Go there and read the extras. Yeah, and we'll talk about anomaly detection. But as everyone does first we do marketing of the person here. So what I do, I teach machine learning at City University, and I do some data munging on Bank of America. So it's mostly data. Enough about me. Anomaly detection is what we came here for. In theory, both sides that we have here, data scientists, hands up, engineers, hands up, are often confused what anomaly detection is. Because one, data scientist cannot figure out if it's supervised or unsupervised learning. Engineers try to figure out, yes, it's probably machine learning, and, well, you will go there, find classification, seems strange. In reality, what this thing is just, we find something normal. Let's say you are at your company loading data into your website from a data warehouse, or anything that you're loading every day in some interval, or every hour, every day. And at some point, let's say 2 weeks in, after you developed your software to load the data in, your boss comes and asks you, today, is the data good? And you scratch your head. Well, we loaded 2 million data rows on a bunch of 100 columns, and well, I have no idea. I have never looked at it. I just look at a couple of rows during the tests. So you don't have a really good way of telling. You just run the application, oh, it failed. So that's often not good enough. So we'll try to use this for such cases, or actually slightly different case with web. All we do is that we check the past. So let's say you loaded data yesterday, you loaded the data before yesterday, and you just do a couple of mathematical tricks to see, is the data close enough to yesterday and before yesterday? If it is, good, it's a normal thing. If it's not, bad, don't load it. So, end of the talk, we are done, yeah? No, okay. So, what we look at, where's the anomaly in there? Yeah, that's easy. Now, I'm not particularly good at biology. So there are flies, there's a spider. But now, if the fly is slowly evolving into the spider is not an anomaly anymore, right? Or even without evolution. Here, spiders and flies are a normal thing. Or even more difficult. Oh, I don't know this one. Actually, most likely the fly in the middle is probably the anomaly there. Humans are good at identifying anomalies, but we'll try now with some data that has more than 5 points. The data we'll look at are basically webserver logs, which kind of look like this. So I just got a honeypot. I started and ran it for a month and a half, and got a little more than 10,000 requests on the honeypot. There's a good chance that people attack honeypots because it kind of looks interesting for an attack. So we'll try to figure out how is likely that one of those connections is an attack. Normal things would kind of look the same. Would normally go through normal HTTP codes, just simple things. Attacks will normally be very complicated, will either look like this. Where's the attacks? I'm pretty confident that strange binary string on a request is an attack. So from this thing, I can argue that the longer the request string is, So the length of that string is a good indicator. But above here we have several other indicators, and most of them are strings. So the first important thing for anomaly detection is that it's machine learning. So it deals mostly with numbers. So we need to transform all this stuff into numbers. And that's actually pretty important, but horribly boring and troublesome. So here's a lot of stuff where we are getting the length, getting the byte counts, getting, well, categorical features, and transforming all this into something that looks more or less like this. On the left-hand side is a categorical feature. So everyone here is kind of aware of HTTP codes. So we have the typical 200 is off the screen, redirects, failures, both types. You have some numbers that can be parsed directly from the file, just ratios, and there's time there on the right. And I cheated a little because I did two representations of time, which doesn't make sense right here. So on the right-hand side is a time that, well, it's just a time series. It's when the request happened during that month and half. The other column, the integer, is the time of the day. So I just took the hour. So the hour there is 3 a.m. is a 3. At the bottom is 5 a.m. is a 5. And that number there at the right is where there is an anomaly. The typical way is to say the -1 is an anomaly, which is likely an attack, and the 1 there is a normal thing. We have about 10%, almost 10% anomalies in there, so almost 1,000. So let's figure out how this looks. Those strings, we transform them in numbers. The interesting bit is that, let me show you the mice. No, will not manage. Second, from the top, at the very right, is the request. Is what we look at where that long string was. Anomalies are normally kind of rare. We have less than 10% here, and they are different. So their anomalies go quite far away in the data. That's the request. There's length of other headers, like the forwarded, like the user agent. And on the right-hand side, the scale is logarithmic. It's a rare thing. The graph looks good, but if the scale was just normal linear scale, you'll just see very small things that you just cannot see. You'll just see one big lump in a single place, and here you can actually see kind of a distribution. The first thing we can do is to treat this as a time series. So we'll just go and pick the thing we looked at before, which is the request, the get, head, and the URL things. And we'll just plot that as a time series. So it's at the very bottom of the time series. The red things is literally the length of that. Nothing else. So it's the length in a logarithmic scale of bytes. Nothing else. The green dots are the anomalies. So I find that, well, there's a lot of green dots in the middle, and that's pretty difficult to figure out why. We are trying to find anomalies. I see there's a normal band in the middle, so most requests are there right in the middle, and that's normal. But there are green dots there. But outside, above, and below, there are only green dots. There's no red dots quite high, and no red dots at all quite at the bottom. They're all anomalies. So pretty much requests that just send, I'm not sending anything. So I'm just checking the connection. Or requests that send that huge amount of bytes are likely anomalies. The other anomalies found there, well, how did I find them? I ran this before, actually ran a different system before to check for my anomalies, and then did some human-made, literally staying on the computer and looking at them if they make sense. And I made a kind of golden truth for the anomalies. And we can then compare whatever we do here, if it would get a similar result to that. Okay? So what we'll try to do is we'll try to measure this band, which is normal, how big it is, and then say everything's above is bad, everything below is bad. We miss a bunch of green points, but to get the green points, we would need to get the headers and do the same with the headers, each of them, and the status, and all other features. Okay, the first thing I don't particularly like there is that the band is big, and we need to measure it. There are two ways. We could try some statistics to find where it goes around, or we could cheat. So we differentiate this. And it looks like this. Differentiating data is trivial. You literally take the value of today minus the value of yesterday, or the previous point. You don't need any complicated maths when the data is discrete. And is mirrored. We can literally throw away the bottom, because when you are getting a different value, then you're subtracting that different value from the next value. So it mirrors. And the bottom there is actually not needed at all. But we can clearly see the anomalies there, right? Yeah? Good. So then there's this thing, an ARIMA, which a lot of people love, and it has a mathematical formulation, etc., but in general is an autoregressive integrative mean average, or a ARIMA seasonal autoregressive integrative mean average extended, and you can add even more terms to that. But in general, it's not much different of looking at the data yesterday, and before, and think what the data should be today. Then you look how the data actually is today. So you got an ARIMA. It will tell you how the data should be today. Then you get the data today. You compare, and you see how it will be different. So in this thing, if I will be saying what's the normal data, I would expect to be always 0, right? On this. If it's in the middle of the band there, then it's a 0 there. Right? Pretty close to 0. So now I get this model and train it. The code is there in the notebook. And I get this. And this seems right, yeah? The red dots are the same as above, and the blue dots are the predictions of the ARIMA. And this seems right. No, it doesn't. We said that around 0 should be all predictions because that's normal. But I see a bunch of dots above. So this is one thing I kind of would like to tell you, because this is the first mistake everyone makes doing anomaly detection. You just throw data at it, which is wrong. ARIMA is a form of detecting novelty. So you can only train it with normal data. So we cheat, we remove the anomalies, we throw away the points that are above, train again, blah, 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 and we have what we expect. So every time you subtract a red dot from a blue dot, and it's considerably different, you have an anomaly. Now we have a bunch of features there, and we need to do it for each of them, for each single feature there. And unless we, let's say, there are 87 features in that log, so we need 87 models, and then we could tell if the data is good. Well, that's still better than that 10,000 rows that we compare by hand, but well, it's still quite expensive. This thing works if you have a single output. So if you have a very well-defined, let's say, price of something, or stock exchange love ARIMA because it have a very well-defined single value. If you have 87 values or 100 values, this can become quite cumbersome. Works fine for 3. And there's some maths. And now we go for some other machine learning that allow us to find those green dots that were in the middle as well. So in a single shot. First thing is, contrary to what we did with ARIMA, so we had one value on x, which was time, and the request. So then we can just compare the values between themselves. Now we have several dimensions. User agent headers often go a lot bigger than the request, or even X forwarded for. I found that there are some headers that actually people dump 4 megabytes in there. So first thing we need to do is scale those things. So then every feature, every piece of the log would have kind of similar values. So then every single, let's say, column in a data frame, as people normally say, would have mean 0 and variance 1. That's very common in machine learning. And then we can figure this out. I said that there are about 10% of anomalies. Well, really 9% of anomalies. So this is literally just getting the labels and taking how many are there anomalies. And we take the baseline. When you do machine learning, you normally try to first try a very, very simple algorithm. So, because, well, they normally don't fail. They are not particularly good, but they don't go off the board and do something completely different. When you do classification, what is typical the algorithm you try first? What? K nearest neighbor, yes. So we'll try K nearest neighbor. But K nearest neighbor in anomaly detection is called local outlier factor. What it does? Well, you have a bunch of anomalies. We have a bunch of features. So the first thing we do, we can argue that every feature we put on a dimension, and then we have a space, let's say 87 dimensions, and each value in each dimension of every row is a point. So every row is a point, and the place where the row is defined by vectors for each feature. So by the length of the request, by the bytes of the request, by the length of the X-forwarded header, by the length of the user agent header, by whether it's a status code 200, whether it's a redirect, all that possible things we can do. Then we have, in that space, kind of a blob of data points, and we can argue that we have normal things that are a blob kind of in the same place. It's just a huge blob of normal things. And anomalies will be somewhere out of the blob, because something will be different. Some value will be either bigger or incredibly smaller, going to the other side of the blob. Yeah, that makes sense? We have a blob and anomalies floating around the blob. So you can do K nearest neighbors. So you take each point, take, let's say here we are using 30 neighbors, measure the distances to 30 neighbors closest, and if the distances are small, that guy is in the blob. If the distances are big, then the guy is outside of the blob. So, very simple algorithm, just K and N, and it goes particularly right. 91%. I would argue that's not that great. Remember, we had about 9% of anomalies. So I say if every single point is not an anomaly, I get 91% right. That's not really true. That's an F1 score. So it actually scores scores that use classes that is just of one type. So if it was not finding any anomalies, this will be almost 0. So it's not that bad, but it's not that great either. That is a baseline. This only is to tell us, now I will try a better algorithm, and I can tell if that better algorithm is performing worse than that, then it's going away and doing something completely different, and that algorithm is useless for my data. Okay, the interesting part is that here is being trained 2 times the local outlier factor. I would allow you to read this on the notebook. At the beginning is being trained as a supervised learning algorithm, and at the bottom is being trained as an unsupervised learning algorithm. So that's an interesting point for data scientists, that most algorithms for anomaly detection works both. both ways. Next algorithm, considerably better. Ooh, that was scary. Considerably better, the isolation forest is better, and it still works from the blob. So you have the blob, but instead of searching for neighbors, you are now taking the features and chopping the features by decision trees, forests. So you dump several trees, and if you can make a leaf of size 1, so you isolate the point from the data set by chopping features on a decision tree, you will have the number of chops you need to do to remove that point from inside the data set. If the point is in the blob, you normally need to quite carefully cut it out of there to remove it. If the point is outside of the blob, you probably can chop it straight away and it goes away. So that's what isolation forest does. And it goes for 99%. But don't believe that much those numbers. They're just a single number to tell us about the full classification. It's normally considerably better to make a confusion matrix. Okay, so we have quite a good measure from about 10,000 points we get most right in the main diagonal. So at the very left upper hand is what we have anomalies as anomalies, so we got it right. At the very bottom in yellow we have normal things that are normal things really, we predicted them right. And on the other diagonal we have false positives and false negatives. Both algorithms, the local outlier factor and the isolation forest, they did do quite not that differently when you do the confusion matrix, despite the local outlier factor is slightly worse. What makes isolation forest a better algorithm is now that you can tune this. So you can, at the cost of false positives, add more false negatives, and vice versa. So if you are putting this thing in production to defend about attacks or checking the data that your boss is asking you, and then this algorithm is throwing a false negative too often, you can have a button, well, improve sensitivity. Or if it's the other way around, and the algorithm just throws a false positives too often, you can just reduce sensitivity. You have class weights on the isolation forest where the chopping can do slightly better. But we'll not be able to talk about that. Okay, so the interesting bits from this talk that I wanted to, well, have people to know, and I rushed through it, so the notebook is important to download, is that we have that idea that some algorithms, like the older ones, like the ARIMA part, if you add the anomalies into the algorithm, the model will work particularly badly. Because those models were used to the fact that you do normal points and you detect just the novelty, what's different. The more machine learning algorithms today, most of them have a way of, you tell them, look, there's about 10% anomalies. So yeah, the algorithm works with that. And the tunability is very important because you want to put this thing in production at the end. So you want more complex algorithms that you can tune one way or the other. And the other is feature extraction. We will jump it. Is always a lot of work. As a closing part, just from the data scientist, one thing I did not do here was PCA. Right? That would be silly if I did PCA here, because one important thing I need to do if this goes wrong, or if it says it's an anomaly, is the question, why? So I need to actually try to figure out what the values of the final features are. And download the notebook, and there are quite a bunch of links. How I did the log, so it's just Nginx format. I just rushed it to ARIMA. So Robert now and Chuk, I think she's doing also a talk later about ARIMA and seasonal points. And the sklearn has documentation about most of these things. Just slightly less text and more practical stuff, so they did it probably better than me. But never mind. So, thank you guys. I hope I bashed at least 3 phrases into it.
Michal, we don't have time for
No,
questions. Will you be around for the rest of the conference?
Yes, absolutely.
You can approach him if you have any question on anomaly detection.
Thank you
again.
Oh, yeah, the